Andrés Luna, who is now at the University of California in Los Angeles again. So the square root of a black hole. Thank you.
So, thanks so much for the introduction. And let me start by thanking the organizers, Lorenzo and Felipe, for putting together this great meeting. I know this is usually part of a script, just thanking the organizers, but in this case I really mean it. Because I know it was a great effort to bring the people and invite me as well, so thanks so much, I really appreciate it. I really like that people are getting interested in this stuff. So I went for the flashy title, what is the square root of a black hole? A better title might have been the classical double copy, a bias review. So I will talk about some ideas that I've been involved with, all of them trying to apply the double copy to classical systems. So about it, this is based on many papers by a lot of people. Most of them are credited. It is not inclusive, so I'm sure I forgot some papers. I hope I don't lose any friends. So it might be a little over-ambitious with my slides, so I will try to go fast, but feel free to stop me. And I will tell you if you want to ask a question in Spanish. I also speak Spanish, so don't be afraid. It's better to speak Spanish than to live with the doubt. So this is a very tough spot. I do have some experience having last or next to last talks, but I have never spoken after a plenary, so it's really difficult. I will do my best. So just to break the ice, around 12 years ago I was in this very room. You can see some of that wall. So that's me. The world looks different now. So Garcia Colin has passed. My hair is no longer that black. Physics looks different. So what happened in the last decade, I think it was marked by two major experimental discoveries. One of them was the Higgs boson, discovered in 2012. The other is gravitational waves, discovered in 2016. It is not surprising that there were Nobel Prizes for both of them. So if you've been here since the morning, you know that the field of scattering amplitudes is closely related to collider physics. After all, it's kind of the origin of why we are computing amplitudes. What is a bit more surprising is what you heard in the last hour, that the field of scattering amplitudes, quantum scattering amplitudes, is somehow related to gravitational waves. So one of the nice things of speaking this late is that a lot of people did the heavy lifting of introducing the subject for me. So I can just give you a brief summary. So what do we do usually to compute scattering amplitudes? Just draw every diagram that can contribute to that process, to a certain order that we want. Apply Feynman rules that comes from a Lagrangian, and sum the value of all of the diagrams. So what is the problem? There are too many diagrams, and even in one single diagram there can be too many terms, as we said. So the name of the game is efficiency. Recycle. You've seen this in a few talks. So one thing that can be done is you can construct big trees. There's a typo there. Out of small trees. Or what has been discussed more, you can compute loop information starting from trees. This is called generalized unitarity. But as someone said, this is nothing that you couldn't achieve if you have infinite time and an infinite number of students. So one of the nicest things about the field of scattering amplitudes is the surprises that were there. so the hidden structures. We heard the last hour about the BCJ double copy. But then the double copy is now used like a generic way to refer to this gravity equals gauge squared paradigm. So there you have some gluons, some amplitudes of gluons, and a collider there. And then you have some amplitudes with gravitons and some astronomical object there, maybe a black hole, I'm not sure. So at some point, someone asked if you could consider also classical solutions coming from the double copy. So there is this paper, 2014, by Chris White, Donald O'Connor, and Ricardo Montero. Chris White was my supervisor in the PhD in Glasgow. So what they do is they start with a family of metrics that are in what is called a Kershel form. This is the graviton. You simply split the metric into a background metric, which is Minkowski, and whatever is on top of that is your graviton. But that, for the Kershel metrics, will factorize as a scalar field and a product of vectors. These vectors have some special properties. Namely, it is null and geodetic. I will not say what is that. But the important part of this is that the Ricci tensor then is linear. So you know, one would expect that you have a lot of nonlinearity in Einstein equation, but because of this, you will have something that is actually linear in the graviton. So what? There you have your linear Ricci tensor. So it was noted by Donald and Chris and Ricardo that if you consider the solution to be stationary, so that every time derivative vanishes, then you can pick some of the components of the Ricci tensor, and so the 0, 0 or the I0 will give you this. If you define a vector field in this form, just as a product of k mu with phi, you can see that these two will ensemble into this equation. So if this equals 0, which is Einstein equation, will imply that the vector field written like this satisfies Maxwell's equation. So you are showing that starting from a gravity solution in some specific form, you can construct a vector field that will satisfy Maxwell-like equations. So what does it have to do with double copy? For the colors help. Funny color palette. So what you heard from Zvi is that you can write the amplitude in gauge theory as a sum of having the numerators which contain all of the kinematic information times the color information, and there you have the propagators. So if you satisfy color kinematics duality, which I forgot there, then you can only strip the color and get a second copy of the kinematic information, and you obtain gravity. So what they found is something similar. You have a vector field. Well, you start here with the metric, and you consider that it has two copies of the vector, which is like a kinematic information, and then the scalar. You construct a vector field which has some color factor there. You keep the scalar without change, and take only one copy of the kinematics. So by seeing this parallel, they argued that this could be a manifestation of the double copy, of the BCJ double copy. In the paper, they have some arguments based, for example, in the self-dual case. And they give some examples with some usual solutions. For example, the Schwarzschild black hole, which can be written in Kershel form. This is just the scalar. There is your vector, which will be null and geodetic. Then they make that double copy-like replacement. And after a gauge transformation, they obtain the Coulomb potential. So if someone asks you, what is the square root of the Schwarzschild black hole? You could say, that's the Coulomb potential. So easy. There are several extensions to this very nice, very specific idea. So the first one, just a few months after the original paper, we looked at the tau-naught space-time. Then nice things happened when some other people start working on the things that you were working. Then we made a lot of other papers. Those are the ones that I've been involved with. But recently, a lot of people have been interested in that, people that I have never heard of. That is always cool. For the people interested in GR in the audience, I would recommend this one because it is not as specific as Kershaw. So this works with type D spacetimes in terms of the Weil spinor, actually. So one of the objections to Kershaw is that it is a very gauge-specific technique, but not for this type D double copy, which is not the Kershaw double copy, but they work as it should work for the overlap. Okay, so when people mention something about double copy and black holes, people say, wouldn't it be cool if we could apply that to gravitational wave problems? So if you were listening a few minutes ago, you know that the part where it could be applicable is the in spiral phase, where you can apply perturbation techniques. But what we have said so far is stationary, so it wouldn't help for an in spiral, and it is also non-perturbative. Okay, so let's think about these two things. So obviously Chris and Ricardo and Donald weren't the first to think about how to relate scattering amplitude slide things with classical solutions. That has been there since the 70s. And one important reference here is a paper by Mike Duff in 72. So what does he do? He computes the vacuum expectation value of the field, which is like one field amplitude, in the presence of sources. These sources are stationary. And he shows that he reproduces to second order in the Newton constant the Schwarzschild solution by applying Feynman rules for gravity. So that's the first order in G. That is the second order in G, corresponds to this graph. But for the third order, he doesn't compute it. And he has this paragraph saying, no attempt is made to compute the 4-point graph or higher order contribution because of the labor involved. So before we mock the guy too much because of that, if we didn't show it full, that is the expanded three-graviton vertex. So the one that had the P3 and the P6 and the sim, that is the full expression. It is 171 terms. Each one of these terms looks like that. And the four-graviton vertex, which would have been needed for the computation back there, has almost 3,000 terms. So being in the 70s, we understand why he didn't do it. So almost 3,000 terms. There you go. Or, as Sheldon would say, gravity. You are a heartless bitch. But you've been sitting here for the last hour, so you know what B says. If you can read the arms, so it's color equals kinematics. So it's color and equals kinematics. Or gravity equals gauge squared. Or doesn't have to be a bitch. Doesn't have to be more difficult than gauge theory. So then we obtained perturbative spacetimes, pretty much like Duff, but from Yang-Mills theory. So going back to something that we said, we don't have to resort to gravity to obtain all of that information, and we can easily, almost back of the envelope, compute all the way to the next order. We define this field which we call the fast graviton, that h, which is like the square of a photon. So how do we do it? Instead of using the 171 terms vertex, we use a double copy vertex, which is just the square of the Yang-Mills. And we compute order by order, perturbatively. And after some computation that I tell you is not that long, we go all the way to third order. But what did we compute here? So for those, it was really clear what was he computing. It's almost obvious because he's doing pure gravity, and this is stationary and spherically symmetric, so it has to be Schwarzschild. But we are not sure what we have here, because what is the theory we are dealing with? So as I said, we have this field that we call a fast graviton, which is like the square of gluons. And a gluon has 2 degrees of freedom. So if you square it, you expect something like 4 degrees of freedom. But we know that the graviton only has 2. That's why it's fat. It has too many degrees of freedom to be a graviton. So then you have to, you have your degrees of freedom. That's the real graviton. That's a dilaton. And that's a anti-symmetric form. And this is something that will be presented. You naively double copy pure Yang-Mills. So then we need a map to split degrees of freedom. So then we can give them in terms of our fat graviton. And we can check if we make an expansion that we are reproducing the first orders of the Janis-Newman-Winnicott solution, which is a solution which has a metric and a scalar field coupled there. So in the limit where you turn off that scalar, that reduces to Schwarzschild. So it is everything perfectly consistent. But this is still stationary, and we want things to move. If we are ever to apply to in spiral black holes, we need things to be moving. We didn't do this. It was Walter Goldberger and Alex Ridgway who first took a step towards that. So what they do is they have a set of equations of motion describing point color charges that couple to gluons. And it's just classical physics. Because these are coupled differential equations, it's very difficult to solve analytically. We don't know if it can be done. But you can just solve perturbatively. So you consider that you have a color chart with an initial state, and then a correction, and you have a position with an initial form, and then a correction. And then you just rewrite your equations of motion, crank the turn. So because they are doing some perturbation thing, you can see that solving the equation of motion, it can be codified by diagrams that look a lot like Feynman diagrams. But this is just doing classical physics. So after obtaining the first contribution to the radiation, they obtain an expression like that. It is in terms of color charges and the velocity of the particles. And they can do the same thing for a gravity theory. Actually, a dilaton gravity. It will be clear why they are doing that. But then you have this, which is like that's Einstein-Hilbert, and then you couple the graviton, the dilaton, and then you have the coupling to the point particles. And again, solve perturbatively your equations of motion and obtain what is the radiation of graviton. So what? Recall from the double copy, what we saw before, that you can have your amplitude for gravity, which has 2 copies of kinematics, and the one for gauge that has color and kinematics. So in principle, you obtain gravity by stripping off color and substituting with kinematics. They propose something like that. This is the expression that I showed you before, and they say that where they see a color charge, they substitute with momentum. And where they see the structure constants, they substitute with the Yang-Mills vertex. They do that substitution, obtain these results, and this contains all dilaton gravity information. So then they say this is a manifestation of the classical double copy. Remember, this is something that came only from classical physics. It's like a word line computation. It does look like color goes to kinematic, but it's a bit different from what we are used to. People kept writing papers about this using the same replacement here. So charge goes to momentum, structure constant goes to vertex. Pretty much all of them are like that. Most of them are Walters. There is some David Chester and Mariana Carrillo and others. But of all of the extensions of this, the nicest one is that one. And I can tell you objectively, not just because this guy is my office mate. This is because he found color kinematics duality in a classical system, which is, if not shocking, at least really, really nice. I don't think we were expecting this to be as nice as it was. But we needed to understand why that happened before. This was not the route that we followed. Instead, we wanted to understand things in terms of amplitudes. So we will compute radiation coming from an amplitude. That's an amplitude for 4 scalars emitting one gluon, or eventually one graviton. What do? We start with a Lagrangian. We use Feynman rules because there are not that many diagrams. This is not so difficult. It's just a 3-level amplitude. Just obtain that amplitude. It is there. Write it in the form that is compatible with BCJ. And we will see that we will have color kinematics duality almost for free. So then we can obtain gravity for free. And from here, we see that taking the classical limits using a large mass expansion, we can reproduce the result for dilaton gravity that was given by Goldberger and Ridgway using Worldline. So this is nice because then it is transparent why it has to work like that. It is just actual double copy, the statement for quantum amplitudes, and then take the large mass expansion. So just after we have used the double copy that is well established, we will take the classical limits. So this was extended to a program to obtain physical observables from scattering amplitudes. This was done by Donald and David Kossauer, who is a longtime collaborator of SV and Lance, and Ben Maybe, who's a student of Donald. So they give this kind of formulas where they carefully define how to obtain the classical limits of the physical observables in terms of the scattering amplitude. That is just the quantum scattering amplitude as we know it, but then you have some systematic framework to translate this into classical information. They do this for the impulse, which is the change of momentum in a scattering process. They do also this for the radiation. You can actually show that by using this systematic framework, we can reproduce what we have here from a much more pragmatic way of taking the classical limits. There have been extensions to this formalism by Guevara Ochoa to the spin case. Also, Donald and Banks and maybe first saw the spin case. So, going back to the title of the talk, so about what is the square root of a rotating black hole. In a recent paper, this is just last summer, which is called Curved Black Holes as Elementary Particles. This is Nimar Kani-Hamed and Jitin Huang and Donald O'Connell. You can show that for the Kershil form, you can have the scalar for Schwarzschild to be of this form. That is just Schwarzschild radius. And you can have the one for Kerr being in this form. So you can see that they are related by a complex shift. Then he, using the Kershel double copy, gives a solution for Young Mills in this form. And he goes beyond that flashy talking about the square root of black holes. He actually started using that root care name. Let's see if it catches. But anyway, using that root care, he shows that, well, just before, this paper about Kerr black holes as elementary particles, it builds on a formalism to give massive spin ortholicity for arbitrary spin. And it winds up relating the minimal coupling, that notion of minimal coupling, which is very different to what one would think minimal coupling is. They relate this minimal coupling to the Kerr black hole, to how the massive particle has to be coupled to behave like a Kerr black hole. And similarly, you can have something which is like the root Kerr, having here the boson to be photons instead of gravitons. So then Donald, using that his formalism, checks what is the impulse for root Kerr and what is the impulse coming from minimal coupling, and he sees that this is the same thing. So this is another link of what we had before, which is the Kershel double copy, to a double copy which is properly one because it's written in terms of scattering amplitudes. There have been some extensions to that in recent literature. Again, this is only last summer, so it's an active area. Yeah, just to mention that there are other classical double copies out there. For example, Jan Plewka along with Jan Steinhoff, they were working on something that goes directly to the effective action. So instead of looking at classical solutions, they go for the effective action, and they try to understand that in terms of the effective action of Young Mills. This is the first paper that they got out. The next one is called a breakdown of the classical double copy, so it didn't last long. There are other things relating directly the classical solutions in a linearized level. This is similar to what we were doing before, solving perturbatively. This is for Young Mills, and it comes from a program that Dove started that wants to relate the symmetries in both theories. So I started saying that wouldn't it be cool to apply to gravitational waves? So now we know that it is cool. We have a whole half a talk about that from SB. I don't say much because you saw it, but they have the 3 p.m., the Tir-Posmikovskian Hamiltonian for binary systems. And not only that, this is also something interesting for the proper LIGO theorists. So people are looking at this. It is a very active area of research right now. So just some conclusions and outlook. So there are several classical manifestations of the double copy. There are some links with black hole dynamics, which make it potentially applicable to gravitational wave astronomy. And the outlook, there's still lots of work to be done, too much to enumerate here, and there are lots of paths to explore. So this is me, thank you.
Thank you very much, Andrés. So we have, yes.
So I think a lot of these square roots of these smooth gravity solutions maybe are more Coulomb or Maxwell solutions than really Yang-Mills solutions. Is that true?
It's true-ish. So what happens is that what we obtain is linearized Yang-Mills, which you can effectively embed into a Maxwell-like solution. So, but this could be an artifact, or it is an artifact of the Kershel ansatz. because Kerfield is linearizing the Ricci tensor. Sure. So I don't have it. There I have it here. So we take that color to be constant, and then when you have the structure constants hitting those color charges, because they are constant and symmetry and anti-symmetry, you kill all of the effects. So yes, it is true that if you are working in this Kerr-Shield frame, you will obtain things that are only linearized Yang-Mills or effectively Maxwell. But there are other ways to approach the classical double copy that will keep all of the information of Yang-Mills.
Because I also heard a talk at QCD Meets Gravity which argued that maybe you needed ghost sources as well to
this was
properly...
by Sylvia? Or?
Yeah.
Yes.
Can you comment on that?
Yeah, so their answers are more complete than what we are considering. So it's similar to what we do at some point there. So we have a double copy here that solves Yang-Mills, and then we square it, and then you obtain gravity. This is only pure Yang-Mills with gluons. But she shows that you can have extended dictionaries, they call it, on how to map the degrees of freedom from Yang-Mills, also including ghosts, to the degrees of freedom of gravity. So one could think of this as being just a more restrictive way of doing double or single copies.
Thank you.
So I think that, what, last one?
Voy a hacer la pregunta en español.
Muy bien.
¿Cuál es el objetivo o el objeto de determinar la raíz cuadrada del agujero negro? Y dos, ¿sí? ¿En qué momento este agujero negro se convierte en un cuásar? ¿O qué tiempo tarda?
Supongo que respondo en español. Sobre el objetivo, la idea es que gravedad es difícil. La gravedad es difícil. Hacer cálculos en gravedad es difícil, porque si uno empieza con un lagrangiano, entonces tiene muchos términos. O las ecuaciones de Einstein son no lineales y están acopladas, etc. Todo el programa de doble copia, su idea es aprovechar que la teoría de norma es mucho menos compleja que la gravedad. Entonces, eso es lo que se quiere aprovechar. Esto posiblemente no es tan útil como lo que está haciendo SB, que es directamente atacar el problema. Aquí nada más estamos divirtiéndonos, jugando con las implicaciones de la doble copia. Quizá no hay un objetivo, la idea era ver cuál era el alcance y quizá en algún momento podríamos aprovechar que la teoría de norma es menos complicada. Entonces, eso. Sobre la segunda pregunta, demostraré mi ignorancia y no voy a decir nada porque no sé, no tengo ni idea de la respuesta a lo que me está preguntando.
So we have to stop because otherwise we're going to run in very late. So we thanks Andrés again.